So one day I was making banana bread, but my oven decided to not anymore, so I had no way of baking anything. Well, it's not that the oven stopped working, it was the stupid control panel that stopped working, which for some reason meant the entire oven was inoperable. Hooray, consumerism, I guess. I mean, I could have technically just burned something on the inside of the oven to generate heat, but I think California has had enough wildfires to deal with. And apparently, oven control panels are really expensive, so it was just cheaper for me to buy a small toaster oven. Which really does go to show how simple of a device a toaster oven is. Electrically inefficient wire to make hot, potentiometer to control how much electricity goes into the make hot wire, and mechanical timer that goes ding so you don't burn your banana bread. Well, I'm not entirely sure how a modern toaster oven works these days, but considering that you could technically design a simple oven like that one, it's not likely that an actual toaster oven would be much more complicated, aside from boring engineering optimizations like wall thickness. Whereas an oven's control panel probably has like 8,000 logic gates just to display the time. So you can kind of see why they'd be within the same price range. Anyways, I bought a small toaster oven to cook my banana bread with the smug satisfaction of knowing that I'd also be saving like 3 cents worth of energy because it takes less energy to heat up small box compared to big box. More on that later. But as you can expect, since I'd never think ahead, my bread tray didn't fit in the toaster oven, so not to be outdone by a small metal box with a glass door, I cooked my banana bread in the small sheet tray that comes with the toaster oven, which surprisingly was just big enough to contain my batter. So while the bread was baking, I realized, hey, wait a second, I kinda know thermodynamics, and this is kind of like the potato thing I thought about a while back. Which, if you're allergic to poorly explained math and physics, seriously, don't watch that video, it's terrible. Basically boils down to objects with a high surface area to volume ratio cooking a lot faster than objects with a lower one, assuming the object's boundaries are held at the same constant temperature. But unlike the potato problem, which consisted of breaking a fixed volume down into smaller shapes to cook, bread is usually baked in one large mass, meaning we're stuck with cooking bread as either one thin sheet or one bread-shaped lump. Since the sheet is much thinner, the center should cook much faster, but how much faster? For simplicity's sake, let's say the sheet has 1/3 of the thickness of the bread loaf. We'll also assume both shapes are perfect rectangular prisms because that's easier to draw, but more importantly, the math is a lot simpler. Also, the bread doesn't rise because that makes everything complicated. And also, the breadsheet is an infinite plane and the bread loaf an infinite line to neglect edge effects like you would in introductory electricity and magnetism with parallel plate capacitors. And the tray doesn't exist because that changes our boundary conditions, so we're not really modeling bread anymore, but the concept should be similar enough, I guess. I mean, yay physics. Luckily for us, physics has this super nice and very simple equation that describes how heat transfer should theoretically take place. Okay, but jokes aside, the heat equation is actually one of the more simpler partial differential equations out there because mathematicians could probably count the number of PDEs they could solve on one hand. So by the merit of having any solution method, it's pretty simple in the world of differential equations. Now, I don't know very much about partial differential equations, so I can't explain this cool method called the similarity solution method, since that would require me being good at explaining hard stuff. But I can tell you the very simple method called separation of variables, not to be confused with separable differential equations because I know I like to confuse those names. Okay, I don't know how I'm gonna do the live section of the video, but hopefully this transitions like well enough. So over here I wrote down the heat equation, and we're just gonna guess that the function u of x and t can be written as the product between two different functions. Theta of t, a function of time, and capital X of x, a function of space. We're using x because that's the notation I used back in school. And we're just going to hope for the best, because all methods to solve partial differential equations involve very systematic guesses to reduce the problem into something that looks like an ordinary differential equation, which we can use very systematic guesses to solve. Anyways, if we plug this guess for u back into the equation, we can take the respective partial derivatives, treating the function of space as a constant when taking the time derivative, and vice versa for the spatial derivative. So for example, we're going to get theta dot, where the dot represents the time derivative, times x is equal to alpha times x double prime, where the prime represents the spatial derivative times theta. And then if we collect like terms on both sides, we're going to get theta dot divided by theta is equal to alpha times x double prime divided by x. And it looks like we haven't accomplished much. The equation looks almost more complicated than the one we had originally. But notice that the left-hand side only depends on time, and the right-hand side only depends on your position, meaning that this equation must equal some constant. I'm going to call it negative k squared, because I already know the answer. We know that this has to be some constant with respect to space and time, because if the left-hand side ever depended on time, then the right-hand side could never equal it for all values it can take. For example, if this was equal to 5 at some time, and this is equal to 5 at some point in space, then we choose a different time where this is 7, but at the same spatial coordinates, this could never equal 5 and 7 at the same time. This essentially means we only have two ordinary differential equations to solve. This one is equal to negative kx squared, and this one is also equal to negative kx squared. Solving these, we'll see that theta is equal to just the exponential function, and x is going to be equal to the Euler exponential function. I'm just going to write cosine, but it's a sum of sines and cosines. And it'll look something like that. And then the rest is going to be an exercise for the viewer because it's just boring plugging in stuff like, oh, look, we have a boundary condition. And then we think it looks something like this. This is why we chose cosine and not sine, blah, blah, blah. Pretty trivial stuff. And as a side note, at least for me when I was solving this, you're just going to have to plug in some arbitrary constant to make the math a little bit easier, but it doesn't really change the process. And you could repeat a similar process for multiple spatial coordinates. The only issue is this expression, let me choose a different color. This expression over here is going to change slightly. So you're going to have something a little bit different when you're solving these equations and when you're solving for k. Like I said, trivial stuff left as an exercise for the viewer. The equations will look slightly different for the sheet and the loaf, but the time-dependent part should look pretty similar, just with different constants in the exponentially part. And as you can guess, the time exponentially part tells us how long it takes for each part of the bread to heat up. So by comparing the two different time-dependent parts of the sheet and the loaf, we see that the sheet should cook at a rate of the thickness ratio squared divided by the difference in relevant dimensions compared to the loaf. Or in the case where the sheet is 1/3 the thickness of the loaf, 4.5 times faster. Boring math aside, it probably would have been easier just to poke the center of the banana bread to see if it was done cooking because mine cooked about 2.8 times faster. Although neglecting the bread rising probably plays into that, and I did overcook my bread, so it probably cooked a little bit faster, I just didn't measure it properly. But this got me thinking, not really, please spare me in the comments. If it's faster to cook bread in a flat sheet, then why do bread loaves exist? Have bakers been part of a global conspiracy to increase human-induced global warming? The thermodynamic inefficiency of bread loaves I've just discussed. But ovens are big boxes of air that need to be heated up to cook one small loaf of bread. It is recommended to preheat ovens, so all that time spent heating up the oven isn't even spent cooking the bread, meaning we spend more time heating up excess air just to get a so-called cooking temperature as heat radiates away. And since electricity for most of the world is just a step away from fossil fuels, this technically contributes to global warming. And we know it's part of a global conspiracy because during the COVID pandemic, when everyone was bored and with nothing to do, what was the first thing that subliminally popped into everyone's mind? Hey, I'll go make some homemade bread. They're already in our head. Okay, back on topic, this method of cooking banana bread clearly saves time, which should also save money. So I'll be comparing cooking a bread loaf in a standard oven to cooking a bread sheet in a toaster oven. Looking at Fourier's law and assuming a toaster oven has roughly similar quality of insulation to a normal oven, and assuming a toaster oven walls are about 1/3 of the thickness, the oven would lose heat at roughly 1/3 the rate that a toaster oven would. As for effective surface area ratio, that kind of depends. If the sides of the oven are twice the length of the toaster oven, it would technically have 4 times the surface area. But this is neglecting the fact that your kitchen probably comes with a nice little cubby for your oven, essentially acting as extra insulation. This extra insulation can be kind of complicated because it could be a pocket of air that doesn't circulate very well, or a slab of cabinet or wall, or a combination of both. Because I can't really be bothered, let's just say that it doubles the effectiveness of the heat insulation that the oven already provides in those areas, meaning we'd have 2 sides of oven without extra insulation and 4 sides with extra insulation, or about 16/3 the effective surface area compared to a toaster oven with half the side length. Along with the fact that my banana bread sheet cooked in about 1/3 of the time a loaf would compared to a traditional bread loaf in big oven, I spent somewhere around 1/5 the energy, or with the theoretical time estimate of 4.5 times faster, I could have expected somewhere around 1/8 of the energy. Now the total energy is dependent on the power consumption of the oven times time. But the problem is that while a toaster oven does technically run at 1 kilowatt, it's not going to be quote-unquote on during that entire time. It's only going to turn on when the temperature drops below a certain value. For my toaster oven, that happened to be roughly 1/3 of the time, or an effective power rating of 330 watts. And with around 1/3 of an hour of cook time, 0.1 kilowatt hours for the toaster oven, and around 0.5 kilowatt hours for the oven with the energy ratio we found earlier. And at 30 cents per kilowatt hour in California, a toaster oven would save about 12 cents per banana bread, meaning it would only take about 200 banana breads to pay off the purchase of a cheap toaster oven, or about 4 years at 1 banana bread per week. Okay, so this is me like 1.5 years after writing the script, or about 6 months after starting this video, which I know took a long time, but I was pretty busy during this period. But I was looking through my notes and thought it would be pretty interesting to add this little bit. So if you're solving the heat equation in 2 dimensions, you might arrive at something that looks like a function of time is equal to some functions of space is equal to some constant. As we mentioned previously, the function of time is going to equal the constant, and these functions of space together are going to equal the same constant. And then if you go a step further, you'll find that the function of x is equal to some constant, and the function of y is equal to some different constant. Because if this function of x ever depended on x, then this function of y never depends on x. So the sum would never equal some constant for like every general case, unless they were both constants. And then depending on the boundary conditions, you can solve for k1 and k2. In the video, I used a square boundary condition, in which case k1 would equal k2. And if you were to go ahead and solve the differential equations, you would get something that looks pretty similar to the one-dimensional case, where you have like k is equal to some function of the length. And in the limiting case, where one of the sides would tend towards infinity, you would find out the temperature gradient in that direction would be equal to like some scaling constant, let's call it beta, divided by L times like some other stuff. But since L is tending towards infinity, the temperature gradient would tend towards 0. Or in other words, if we were to take this square and stretch out one of the sides to infinity, the temperature gradient in that direction is negligible. K tends towards 0, meaning that one of these guys, depending on whichever one you let tend towards infinity, would go to 0, and you would just get the one-dimensional case again, which we can see here because this is basically the infinite plane. So just a quick sanity check.